So, good morning, everyone. My name is Claudia, and I'm going to present the work Kinematics and Gas Excitation in Galaxies with OH megamaser emission. Galaxies are huge cosmic islands of stars, dust, gas, and dark matter held together by gravity. They can be of different size and shapes, and Hubble in 1926, based on morphological characteristics, classified the galaxies in four large groups: elliptical galaxies, spiral galaxies, lenticular, and irregular. Galaxies can be isolated in the universe or in small groups, in clusters, and even in superclusters. They interact with each other and can even merge. In these interaction, galaxies are an important reference for the study of galaxy evolution. Ultraluminous infrared galaxies typically consist of galaxy interactions and mergers. They are objects extremely bright in the infrared wavelength and with luminosities in the infrared above 10 to the power of 11 solar luminosities for LIRGs, and above 10 to the power of 12 solar luminosities for LIRGs. They are believed to represent a key step in the process of transformation and evolution of galaxies, and their extreme luminosity in the infrared may be associated with intense star formation, which we call starbursts, and or the presence of an active galaxy nucleus. This is the LIRG RP 220. It's the nearest LIRG to the Earth. So what are these AGN and starbursts? AGN, or active galaxy nucleus, are galaxies whose central region emits very large amounts of energy with a non-thermal spectrum. The energy source comes from gas being accelerated by a supermassive black hole at the center of the galaxy. Starbursts are not a type of galaxy, a class of galaxy, but a phase which galaxies can pass through where intense star formation occurs, typically between 10 and 300 solar masses per year. To compare, our galaxy Milky Way has a rate of star formation less than 2 solar masses per year. Starbursts are often quite bright in the infrared because of the large amounts of dust, which absorbs ultraviolet radiation, heats it up, and re-emits it as thermal radiation in the infrared. The maser is a microwave amplification by stimulated emission of radiation. It's similar to a laser, but instead of light amplification, it's microwave amplification. Megamasers then are luminous extragalactic masers with luminosities between 10 to the power of 2 and 4 solar luminosities, 100 million times brighter than masers found in the Milky Way. They have that name because amplified spectral line is due to transitions in the hydroxyl molecule. They are associated with galaxy interaction and merger environments, and consequently with LIRGs. And many OHM host systems present composite spectrum, both with characteristics of starburst and AGN. A possible explanation for that is that galaxies with OHM would represent a transitional stage between starburst and AGN. So the project has the general objective of relating the properties of the OHM and the state of merger and interaction of the host galaxy to the AGN and or starburst activities. It has a subsample of 15 galaxies with OH megamaser emission, and the data comes from three observatories: Gemini Observatory, Hubble Space Telescope, and VLA. 7 galaxies in the sample have been studied so far, and in 6 of them, the presence of AGNs was detected. In addition, the presence of circumnuclear star formation regions was also detected in most galaxies. The general objectives is adjust the emission lines present in the spectra of galaxies in order to obtain measurements of gas fluxes, velocities, and dispersion of velocities. Determine from line radial maps and diagnostic diagrams whether the mechanism of gas ionization in these galaxies is due to the presence of regions of intense star formation, the starbursts, or to the presence of an AGN. Detect the existence and estimate rates of ionized gas outflows in the galaxies, and finally propose a scenario that justifies the presence of the megamaser emission. So as I said, the data comes from 3 observatories, but until now I only worked with data from Gemini Observatory. And when I get access to this data, they are not ready to work, so I have to make this process that is called data reduction, which is a multi-step process with the aim of make raw data readable for work. It is made with IDAF software, astronomical data reduction and analysis software IDAF. And the final product of the data reduction is the data cube, which is 3-dimensional. It has 2 spatial dimensions and 1 dimension corresponding to a range of wavelengths. The 15 galaxies in the subsample, of the 15 galaxies, 13 has already been observed, 7 has already been studied, 3 by me, and 6 has already with reduced data ready for analysis. There's an image of the data cube, so I work especially with this spectrum here, adjusting these lines. The methodology is with the EFS cube, which allow me to perform the gas, to obtain a gas distribution and kinematics, which is fitting of Gaussian curves and Gauss-Hermite series to the profiles of the emission lines present in the spectra of the galaxies. This process returns 2-dimensional maps of flux distributions, velocity fields, velocity dispersions of the gas for each fitted emission line. And another step is the gas excitation mechanism, which is the construction of 1 and BPT diagnostic diagrams. It allows distinction as to whether the source of ionization of the gas is due to a star-forming region and or an AGN. Here are some results that I'm going to talk more about in my next talk. But here in the left are the maps of fluxes, velocities, and velocity dispersions. And in the left, the diagnostic diagrams, in this case, 1 diagnostic diagram. That's it. Thanks for listening.